And before we show the results, we measure the optimal list of travel cities and priorities. But before that, we need some key parameters. So we estimate the model parameters using data from confirmed COVID-19 case in China, and we measure that at the city level. And in measuring this, because we know the transportation and the transmission of virus from all the city J to city I could be endogenous. So that's why we followed our published work in Journal of Population Economics to instrument those two endogenous variables, which is the number of people traveling between from J to I, and the transmission number of people infected within city I, the home city, and also the weighted average of this the travel strength between city J, all city J to city I, and the infection in city J. This shows like a weighted average of all the transmission from all possible city J, which has linked with city I. And we use that, we use ZJ as instrument. ZJ is the local weather conditions. So the ZJ means the weather condition of city J. Because we know weather pattern is a critical factor of like precipitation, temperature. Those are the major factors in fact affecting the transmission in city J, and which may through city J and through the transportation may affect the link to city I, and the weather in city J should have no direct correlation with the transmission in city I, which is YI. And here is the estimates. So here shows that this is we just show you the OAS estimates and our instrument variable estimates, which shows the causal inference estimates are very similar, slightly larger because there might be some reverse correlation effect, which drive up a little bit this parameter. But this 0.258 means that a 1% increase in infection in a city J, where 100,000 people travel to the city I, will cause 0.258% increase in the number of cases in city I. So which give us the transmission number, the parameter. This is number is a critical parameter for us to evaluate the coordination, non-coordination, and the welfare effects. And we also use model B. We can skip up about that, but this model B is using a different sample. We just want to show the robustness, and because model B was using the sample before the Wuhan lockdown, so the travel was not even being affected by the concern of the virus spreading. So during that time, the infection should be more exogenous. But basically, they show us very similar results. Now, let's think about it as a governor or as a social planner of the economy. We need to weigh the balance between reducing the infection for every city I. So overall, there are 360 city I in the sample, in our sample. So we want to have smaller this term. And this term shows the Wij is the travel between city I and city J. And here is the, this term shows the average cost of this travel. So we also want to mitigate this term because with more travel restriction here, so the phi ij is the size of restriction, so ranging from 0 to 1. 1 means that the travel between city J and city I was not affected, but if equals 0 means the travel between city I and city J is banned. And this second term is economic cost. The first term we can think of as the public cost, public health cost. We try to minimize the overall two terms together. And we can solve this. And if you're interested in this understanding how we derived this model. We can skip this